any question or concern, please do not hesitate to ask Vesna or the organizers. And let's start with the first talk. Marco de Renzi, and we're looking forward to your talk.
Thank you very much. So, yes, I'd like to thank Christophe, Azad, all the organizers for inviting me to give this mini course and for organizing this conference. It's a pleasure to be here. And in this series of talks, I will discuss three-dimensional topological quantum field theories. From what I understand, the audience is quite diverse semantically. So maybe it's good to start by explaining what I mean by topological quantum field theories. And yes, so TQFTs, which is short for topological quantum field theories, first appeared in the works of theoretical physicists like Schwarz and Witten, but they were formalized in mathematical terms by Michael Atiyah towards the end of the 80s. And by paraphrasing the original definition of Atiyah into slightly more modern terms, we can say that a TQFT can be defined as, okay, I will give an abstract definition, as a braided monoidal functor from the category of n-dimensional cobordisms to the category of K vector spaces for some field K. And okay, this is quite abstract, so it can be translated into more concrete terms. So concretely, a TQFT in dimension n associates, okay, maybe I will do like this. This is not working right now. Okay. Associates with every closed n-1 dimensional manifold K vector space, which we call the state space of the manifold. Is the space of states for the space Y, like this. And to every n-dimensional cobordism, which is an n-dimensional manifold whose boundary is identified with the disjoint union of Y and Y prime, two spaces, TQFT associates a K-linear map, which you can think about as a time evolution operator between the state spaces. And TQFT does so while translating the topological operation of gluing of cobordisms into the algebraic operation of composition of linear maps. And this joint union is translated into tensor product. And this is a topological quantum field theory in the sense that there is no metric, for instance, that intervenes in this definition. Only the topology of space and the chunk of space-time between Y and Y prime plays a role in the definition of a TQFT. And I will try to explain in a second why should we care, why do some people care about this kind of notion. But before doing this, let me use a few moments to provide some comments. First of all, I know virtually no really interesting examples of TQFTs that fit precisely this definition if we take it literally. And this is because examples of TQFTs, concrete ones, do exist, and interesting ones do exist, but they typically require either some additional structure, maybe very mild, but some additional structure on cobordisms, or maybe some conditions for TQFTs to be defined. Additional structures could be very mild, like some homological information attached to these cubordisms, or maybe some decoration like some knot or link or a tangle or a graph embedded inside these cubordisms. Or these cubordisms might be subject to certain conditions. So for instance, certain TQFTs might be just partially defined on a category of cubordisms. And we would still like to call the result a TQFT because we would like to be flexible about this definition. So I will change this. I wrote, let's say, a category of n-dimensional cubordisms. Different choices can be made, and they all deserve the name TQFT. And I will also be flexible about the target here. Instead of the category of vector spaces, we will allow ourselves, according to the structures that exist on cubordisms, to maybe choose different targets. Maybe vector spaces are equipped with the grading given provided by a group, or maybe the action of some algebra, and cubordisms might preserve the grading or intertwine the actions of this algebra. And again, we would like to call all the resulting notions TQFTs. And not only this, so in this series of talks, I would also like to discuss a more general notion of TQFTs, a higher categorical one, which I will call extended TQFTs. So I will add an E here in red. E is for extended TQFT. And the definition is kind of the same. So an extended TQFT can be defined in abstract terms as a graded monoidal where we need to go at least one categorical level higher. So we're talking about two factors here from, well, let's say a two category of n-dimensional cubordisms to a two category of, well, the analog of the K vector spaces, one categorical level higher, is K linear categories. And I will explain what this means in a series of talks, but for the moment, we can just have some schematics like the one we had here. And in the case of extended TQFTs, well, closed n-2 dimensional manifolds are sent to K linear categories. And n-1 dimensional cubordisms are sent to K-linear functors, and n-dimensional cubordisms with coordinates this time are sent to natural transformations. I'm drawing pictures here in dimension n=2 because this is the case where we don't need to make any simplification to visualize things, but we will focus during this week about dimension on dimension n=3. And again, here we're translating gluing to composition and disjoint tensor, right? And maybe now it's the time to address the question of why should we care about these things? And from the point of view of topology, so yes.
So the toroidal zero would have satisfied your original conditions, right? Semi-simple toroidal zero.
Yes. Toroidal zero doesn't require any extra structure, and
you're saying yes, you want more interesting TQFTs.
Yes, you're right. So I'm just going to focus on a general construction this week for which some extra, very mild extra structure is required, and which is more in the spirit of Reshetikis variety. And also some conditions are required, and also there are more general notions of extended TQFTs. You can consider fully extended theories, which go even higher in the categorical ladder. But here, the general construction I will discuss in general stops at the floor just above standard TQFTs. So to me, extended TQFTs will just be in this sense. But yes, you're right. So why should we care? From the point of view of topology, which might not be the point of view of everyone, but from the point of view of topology, there are various reasons to like TQFTs. TQFTs provide topological invariants that can be computed by cut and paste methods, for instance. Say you have an invariant of some closed manifold, here is a two-dimensional manifold, and say this invariant comes from a TQFT, then what you can do to compute it is you can slice your manifold into simpler pieces, and the TQFT will associate linear data to all these pieces, and the global invariant can be computed by composing and tensoring the linear pieces associated to simpler topological cobordisms. And so these are invariants that can be computed by cut and paste methods. They can be quite powerful invariants, so quite good at distinguishing manifolds. For instance, there exist TQFTs that contain invariants that, like the abelian-Rademacher torsion, that classify length spaces, recover the classification of length spaces. These are a class of three manifolds that are kind of subtle to distinguish. And not only we have scalar invariants of closed manifolds that can be computed like this, we also get more general invariants that we like. So let me write down here what I just said. So motivation. I talked about closed, so in topological invariants. Of closed n-dimensional manifolds. Then I talked about, then I will talk about mapping plus group representations. For n-1, dimensional manifolds. Because the TQFT also provides somewhat more refined invariants for even n-1 dimensional manifolds, like representations of the mapping class groups. And the ones we get from TQFTs in concrete examples can have very nice properties. So they can preserve Hermitian pairings, they can be restricted to integral lattices inside complex state spaces for surfaces in dimension 3. And then they can admit like homological models based on the twisted homology of configuration spaces of surfaces. And all these properties can be used to do some topology with the invariants and the representations that come from TQFTs. And there are people at this conference that work on this. So these are reasons why people in topology like TQFTs, but this is not the only point about TQFTs. Maybe what is most important is they share deep relations with other fields. So one of the main themes of the conference will be the relation between three-dimensional TQFTs and two-dimensional conformal field theories. We have another mini course about this. So we have relations with CFTs, but also representation theory in general. And but also geometry and physics, since the deepest conjecture in the field come from relation from predictions that come from physics or relation with geometry, and so really this is the real recurrence of the theory of TQFTs, and this is why we will focus on three-dimensional TQFTs during these talks. And so I've shown basically what I wanted to show for the beginning on these slides. And maybe I will try to turn this on and use this. And so now let me state what would be my goal for the week. So the main goal will be to explain how every modular category C induces an extended TQFT, which I will denote A hat sub C from a certain two category, which I will denote like this, to a certain two category that I will denote like this. And the goal will be to explain everything that I'm writing down. And this TQFT has the property that it extends the curl of Lubashenko TQFT, which is a functor like this that is defined on another category that I will also introduce and with values in C. So, as I said, so the goal will be for me to explain everything that goes into the statement, tell you more precisely what an extended TQFT is. I will tell you what a modular category is. This I will do today. This I will probably do tomorrow. I will tell you what these two categories that appear here, what they are. This is a subcategory of the full two category of is a sub two category of the full two category of three-dimensional cobordisms. This is a certain category of suitably complete linear categories. And this construction over here, well, although this will be the ultimate goal, I will spend most of the time explaining how to define this one, which is a construction due to Keller and Lubashenko and dates back at least 25 years. And it's defined on a somewhat strange category of cobordisms that is not really of the sort I described there, but I will try to explain how this fits into the framework. And the target is not vector spaces, is the modular category itself that we're considering as a building block for the theory. So the goal today for me, at least, will be to explain a little bit definition of the categories that appear here, except for maybe modular categories, which will arrive tomorrow. But at any time, if I'm saying things that are not very clear, please feel free to stop me and I can try to give more details. So now I should start with the main part. And I will start by trying to make sure that we're on the same page about braided monoidal categories. What is a braided monoidal category? Because TQFTs are defined as functors between braided monoidal categories. So a braided monoidal category is a category C, which comes equipped with a few pieces of structure. So a tensor product, a tensor unit, and braiding. So a category, okay. You've already seen a modular braided monoidal categories if you've attended the previous weeks of this conference, but maybe not everyone has. A category is a class of objects, and for each pair of objects, you have a set of morphisms between them that can be composed. And in a monoidal category, you have the notion of a tensor product, which allows you to tensor together objects and morphisms. You have a tensor unit, which plays the role of the unit for this product. And the braiding is a natural isomorphism between the tensor product and the opposite tensor product. And all these pieces of structure are come together with more pieces of structure. We have plus coherence data. But the point of this week will not be to know all the details of these definitions if you don't already know them. It'll be enough just to know that what are the consequences of these of the presence of this coherence data. Concretely, what we have once we have a braided model category is a way of representing diagrammatically morphisms in this category, and especially the braiding. The braiding in a braided model category can be represented as a crossing. What do I mean by this? So in a diagrammatic language, you can understand, you can represent tensor product as horizontal juxtaposition. So when I write x and x prime, one next to the other, you can understand this as the object x tensor x prime. And you can represent morphisms between objects as diagrams that can be read from bottom to top. So this would be a diagram that goes from x tensor x prime to x prime tensor x. And the coherence data satisfy so that we equipped our category with for the braiding will tell you that if you represent the braiding as a crossing, then you have a diagrammatic calculus which is invariant under well, most of the isotopies, Reidemeister 2 and 3 moves. Which completely means this, if you don't know what I mean. So the braiding is invertible, so it has an inverse, which is the other crossing. And this is some sort of isotopy you can see between these two tangles. And it also satisfies this other famous relation. So whenever you have a braiding on a monoidal category, you can represent it as a crossing in the diagram, and it will satisfy automatically these conditions by the coherence data it comes with. The coherence data is subject to certain coherence axioms, and if you consider the analog notion one categorical level higher, then you talk about braided monoidal 2 categories, and they are kind of the same thing. They are just 2 categories that come with a tensor product. This would be a 2-functor instead of a functor. Tensor unit will always be an object. The braiding will be a transformation between the tensor product and the opposite one. This T here is just the permutation, the transposition of the 2 components of C here. So I haven't explained this, but this maybe makes it more clear. And the coherence data becomes higher coherence data. The axiom it satisfies becomes even higher coherence data that satisfies even higher coherence axioms. All of this will not be important. What is important here is that once you have a braided monoidal category, you can tensor together objects and morphisms, and you can braid them. So you can have isomorphism between the tensor product and the opposite. And a braided monoidal functor between braided monoidal categories will be, well, a functor that is equipped with an isomorphism between well, the tensor product of the images and the image of the tensor product. It also has another isomorphism that identifies the tensor unit of the image with the image of the tensor unit of the source category. And again, so basically, a braided monoidal functor will be a functor that behaves well with respect to the extra structure we have on braided monoidal categories. It translates the tensor product of the source to the tensor product of the target and the tensor units too, and it behaves well with respect to the braidings. This all goes into the higher coherence data that's here, and the same holds for one categorical level higher. And maybe, okay, if you're not already familiar with this, this might be, again, a little bit abstract. The only takeaway from these two definitions is that in braided monoidal categories and two categories, we can tensor together objects and morphisms. We have isomorphisms between tensor products and opposite tensor products. And once we look at braided monoidal functors and two functors, while these allow us to map braided monoidal categories between them, respecting all these operations. And now maybe I can tell you what is...
So why braided? I mean, shouldn't be...
Yes, so in the higher coherence data we have here, there is, so either it's an axiom that is satisfied in the so for standard categories, there is an axiom that will tell you that the image of the braiding is the braiding of the images. And so one categorical level higher, this axiom becomes a new piece of data, of coherence data you need to add to a monoidal functor, and it will satisfy higher coherence requirements. Again, yes, so here there is a condition that tells you that the braidings are but it will not be a natural isomorphism. It will be an axiom in the case of standard categories, and it will be a modification in the case of two categories. It will not be very, so, I mean, you can just think about the fact that we map braided monoidal categories by preserving all the additional structure we have on them. And maybe now I can tell you what is the target in our goal here, this two category cap with a hat. Okay. This, by definition, is going to be a category with objects. Well, okay, let me write it down. Finitely complete K-linear categories. K-linear categories are categories where morphism spaces carry the structure of a K-linear vector space such that the composition becomes a bilinear map. And finitely complete categories are, okay, this is the appropriate notion of completeness we need for this construction that I will explain to produce an extended TQFT. It will not be important to know what finitely complete categories are if you don't already know. So for the purpose of this week, I will just talk about linear categories. And then there is a procedure to add all finite limits to a linear category to make it finitely complete. And this will be required to get an extended TQFT. But the main point here is that we will map n-2 dimensional objects. So when n equals 3, is one-dimensional manifold. So circles will be mapped by our extended TQFT to linear categories. One morphisms. Which are morphisms between objects will be sent to left exact K-linear functors. Again, the main point is that they are linear functors. Left exact are the continuous one for finite complete categories. They preserve all finite limits. And three-dimensional cobordisms, so two morphisms, are sent just to natural transformations. Between these functors, natural transformation are essentially the same thing as we don't need to add K-linear here because the condition is always met. Right, so this will kind of be the target where we will represent. So we can think about the TQFT as some sort of linear representation of a category of cobordisms, and we will represent the one over there in this two category. In this two category, we have a tensor product. Which I will denote like this, is the box product is a tensor product that satisfies a universal condition for finitely complete linear categories. And yes, I think it was introduced by Kelly. And but you just need to know that it's universal in the sense that it provides an isomorphism between those functors from a product of two K-linear categories, which are left exact in both variables, and the left exact linear functors from this box tensor product. And there is a tensor unit in this category, which is the finite completion of the well, trivial unit K-linear category. So this is the category of vector spaces, finite dimensional vector spaces over K. This is where we will send, for instance, the empty object of the category of cobordisms to the category of vector spaces, and the braiding is induced by transposition, and it's symmetric. So basically, again, here maybe if you're not familiar with the language used here, the main takeaway is that we send, as I kind of tried to explain at the beginning, we send circles or disjoint union of circles to linear categories. Surfaces with boundary are sent to functors between the categories attached to these circles, and three-dimensional cobordisms are sent to natural transformations between these. And what are, so let me make sure that it's clear what an n-dimensional cobordism is. So an n-cobordism will be denoted like this. And it's given by an n-dimensional manifold a pair of n-1 dimensional manifolds. I will take some space here. Because I will add something in a second. And these should be equipped with, so like the boundary of X should be decomposed to an incoming piece and an outgoing piece, the incoming boundary and the outgoing boundary, and the incoming boundary with opposite orientation has to be identified explicitly with the n-1 manifold y, the outgoing boundary with y prime. And so a cobordism is all of these informations packaged together, not just a manifold, but also a partition of its boundary into two portions. One which is explicitly identified by an explicit diffeomorphism with y, and the other which is identified with y prime. And a cobordism with corners is the same thing, but between cobordisms. So let's say that you want to explain one. So cobordism with corners, we always use the same notation here. X is an n-manifold with corners. Y and y prime here are cobordisms themselves between n-2 dimensional manifolds. So you see here, instead of manifold, we have cobordisms. And okay, so in a manifold with corner, you have the notion of horizontal boundary and vertical boundary. So this time it's the horizontal boundary that should be identified with two cobordisms given, and you have analog identifications for the vertical boundary of X that should be identified. So this should be identified with Z times the interval. And this with Z prime. And okay, maybe this would have been, okay, it would have been nice to show again the pictures I had at the beginning, where I made an example of a cobordism with corners. Okay, it's not very convenient to switch back on the slides, but basically I made a simpler example like this. The cobordism with corners, you have a manifold with corner whose horizontal boundaries are identified with maybe y reverse orientation and y prime, and whose vertical boundaries are identified with z and z prime, here opposite orientation, and both you take cross an interval, so you take trivial vertical boundaries. And with this, you can define the two category. Three-dimensional cobordisms. This is going to be the two category. Objects denoted gamma. These are just closed one manifolds. One morphisms. From gamma to gamma prime. are going to be okay. In the concrete examples, we will in the examples we will consider over this week, we need this little piece of extra structure on morphisms. So they are going to be cobordisms, so two-dimensional cobordisms equipped with a certain subspace of their first homology with real coefficients. This is not really important. It's a Lagrangian subspace with respect to the symplectic intersection form that you have on these real vector spaces, the first homology. And here I'm giving precise definitions with finitely complete, left exact, etc. And here I'm making it explicit these subspaces because I want to make that into a true statement. But for the purposes of the talk, we will of the talks this week, we will not pay too much attention to this mild extra structure. It will be.
I don't need to worry about the boundary, like something happening at the boundary for this.
Yeah, so the boundary will always be part of this Lagrangian. So the boundary of surface with boundary is always in the kernel for the intersection pairing. So every Lagrangian subspace contains the homology of the boundary.
I don't need to impose some condition at that boundary.
You don't need to impose anything. And anyway, so my goal, I don't know if I will manage, but my goal is to tell you more explicitly about the lower category you have there, cobordisms with a C and a Y. These are craniatal cobordisms. We are going to visualize them very explicitly by diagrams, and these diagrams kind of encode already all this extra structure without need to further comments. So if you will be happy with the diagrammatic description I will give later, you don't need to, so it will already contain all this information without the need to make to give more details here. So if you've never seen these things, don't worry, they will go away in a second. So and two morphisms are going to be equivalence classes. Of triples. Sorry, pairs. M and N, where M is a cobordism with corners. You can see my sigma prime, free cobordism. And N is just an integer, called a signature. And as I said, we have here that the tensor product is induced by disjoint union. The tensor unit is just the empty circle, so like the empty one-dimensional manifold, and braiding is just induced by re-indexing. Components in a disjoint union. Yes.
So the vertical boundary, I suppose maybe I could think about this as some kind of like collar. Should I think about that?
So for you mean the vertical boundary, you said?
Yeah, the vertical boundaries.
Yeah, the vertical boundaries are always cylinders over the corners.
Yeah.
Yeah.
So I just think about this as like choosing a collar.
Yeah. So you can think about, but it's kind of nice to keep the corners in place to allow for smooth compositions both horizontally and vertically. But yes, topologically, this is just a color of the.
Okay, so can you do it with actually pinching that vertical boundary? Is that possible, or you can't do that?
It's better to keep them expanded in such a way that the horizontal composition is really along a surface and not. Otherwise, I mean, if you pinch, then you need to consider a color and glue along the color anyway. So yeah, but topologically, this, if you don't take care about the smooth structures, yes, this is the same as pinching them. Yes. So, and now maybe I can say what non-compact cobordism is. Maybe I will erase here. Because here we are talking about non-compact cobordisms. So a cobordism is non-compact. And also cobordism with corners. So this also with corners. It's non-compact. If all its connected components have non-empty outgoing boundary. Outgoing boundary, or in the case of cobordism with corners, outgoing horizontal boundary. So in the picture over there, a cobordism Y is non-compact if its intersection with Z prime is non-trivial for all its connected components, and the cobordism with corners X is non-compact if all its connected components intersect Y prime. And the TQFTs we're going to construct this week, they are in general only defined on the sub-2 category of 3 cob, called 3 cob and C is the sub-2 category of 3 cob with morphisms. Are non-compact. Both one morphisms and 2 morphisms.
Why does it call non-compact?
So I think right. So yes, this is a good remark. So I'm using here, for instance, connected components in the topological sense, meaning really I'm talking about connected components of manifolds, and non-compact. Every manifold I'm considering here is always compact. I think the terminology dates back to Lurie, so who worked on the cobordism hypothesis and who gave the name non-compact to this subcategory of cobordisms. But you're right. So the cobordisms here, everything is compact. Everything inside is compact. But yeah. So this is why I'm giving a definition here. So non-compact meant in this sense is every connected component has non-empty outgoing boundary. And
maybe a comment on the question. So apparently this terminology non-compact comes from non-compact sigma models.
okay.
That's
So
what I
first, from something else which is non-compact.
So sigma models with a non-compact target, apparently, that's what I was told at one point at least.
Anyway, so this is you can choose other names. Maybe I'm using the one that has been chosen by Nuri, and which has been taken up by people doing three-dimensional TQFTs recently in the papers by François Costantino, Nathan Gear, Bertrand Patureau, and Benjamin Ayoun. Also, yes.
If the TQFT is non-compact, is there still a way to assign an invariant to a closed manifold somehow?
Well, no. I mean, it will associate invariants to at most. Well, we will see there is a way of extending this to also closed three manifolds, but you need to allow for decorations inside these manifolds. You need, for instance, to equip them with some links or graphs, and you need some condition on these graphs. In particular, if your category C you're working with is not semi-simple, then you need these links and graphs to be non-empty, and you need some projective color somewhere on these. Okay. So this is a way of extending to closed manifolds, but otherwise, the way I'm stating it right now, no.
I mean, depending on the circle value, won't you, I could just like take a closed three manifold, scoop out a ball, and then I get this non-compact boardism, and then
Yes.
I get some kind of invariant.
Yeah. Okay, of course.
I mean, it's not as detailed as the thing you're talking about, but
Yeah. So you can think still about closed three manifolds if you consider a cobordism from, let's say, the disk to the disk, and you consider that there is a unique way of filling it to a closed manifold. Yes, you can understand this as being an invariant of a closed manifold.
How can it be a subcategory if you compose non-compact? You can have compact pieces in the compositions.
Well, no, this cannot produce. This cannot produce. No, because we completely disallow cobordisms that have connected components that are disjoint from the outgoing graph. So you can never.
You just have two pieces like that, and then you compose them, and then
You don't have the other piece. You have this piece, but you don't have the other in your category.
direction.
I'm forbidding them. So, and the category appearing here, the craniator category, is the subcategory of this category over here. So cobordisms from empty to S1, and one morphisms and two morphisms here, which are objects and morphisms of this category, they form a category, which the subcategory of this whose objects and morphisms are connected is called the craniator category of cobordisms. CY is for craniator. And a small remark, this is I think I'm doing very badly with time. Yes, I have 2 minutes and I have the, okay, so I will postpone to tomorrow the description of this category. But let me just say one thing now. This is a braided monoidal category that has a different braided monoidal structure with respect to the one above. So remark. So it's a braided monoidal category, but not a braided monoidal subcategory. So 3 of craniator is a braided monoidal category with tensor product given by disjoint union, which is induced by the following two-dimensional cobordism. So a pair of pants, if you understand this as a cobordism from two circles to a single circle, will give you a tensor product on this category. You just have two objects here. Objects here are two-dimensional cobordisms from empty to circle. So they are surfaces with one boundary component. And you can glue them here to get a new surface with one boundary component. And it's a braided monoidal category. And braiding, C, induced by this cobordism with corners. This is a cobordism with corners that kind of braids the tensor product. And this braiding is non-symmetrical. So it's not symmetric. So it's a non-trivial braiding. And I'm taking your question in a second, but just wanted to highlight, to explicitly say that this is a braided monoidal category naturally, but it's not a braided monoidal subcategory of this. So the tensor product is different. The braiding is different from the ambient 2 category. I'm introducing this category this way because my initial definition of TQFT does not include immediately categories like this, but these are a natural piece of the ambient 2 category in an extended TQFT, and these are the main piece, I would argue. So the construction I want to tell this week, I want to explain this week, starts from functor, braided monoidal functor defined here, and then you can extend it to the rest of the 2 category. But kind of this is the main, so the starting point. So tomorrow I will try to convince you that objects and morphisms in this category can be represented by diagrams, and everything becomes really diagrammatic, and we can understand all the rest of the construction in terms of these diagrams, and so everything will become very visual. So you had a question?
As objects, you can have multiple disks, right?
Sorry?
As objects, you can have multiple disks, right?
So in the big 2 category, yes, and here objects are surfaces.
Yeah, but they're surfaces, but they're disks in particular. But my question is about the product on the category is like a disjoint union of disks, right?
So yeah, the tensor product in this category would be, so between a pair of disks would be the disjoint union of the 2 disks. And here the tensor product I'm considering is different, is boundary connected sum. So the tensor product between 2 surfaces with a circle boundary component is another surface with a circle boundary component, which is obtained by gluing them here. And the topological operation underneath this is a boundary connected sum.
Yeah, let's first thank Marco for this very nice lectures. We already had a smooth transition to the discussion session. So are there more questions?
So I have one. So I'm not very used to this Kelly product of complete categories, and I assume it always exists.
Yes, for finitely complete categories, yes. Yes. And when the category is abelian, it's the same as the Deligne tensor product of the 2 categories, when it's a finite abelian category.
There are no more immediate questions. I'm sure we can ask questions to Marco during the break. We will continue then with Ingo's talk in 30 minutes, right? Or right away?
Let's say this way.
Sorry?
Yeah, I think so.
Yeah.
Right, 11:30.
I didn't look up the schedule, but let's have a coffee break. Thanks.